Hello everyone, my name is Anggitraksajati. In this video, I'm going to present you the development of block diagram for the DME synthesis from methanol. Okay, so let's start with the development of the block diagram and the operating condition for each of the main equipment. All the important information is already provided at the top of your screen, starting from the condition of your feed, and then this is the expression for the reaction, including the power law equation, and then you have the specification for the product, and at the right corner of your screen, it is for the utility available. And remember, from the onion diagram that we talked in the previous video, we always start from the inner layer of the onion, which is the reactor. In that case, we will start with the reactor. So I'm just going to write a block over here, which will be our reactor. And there are a lot of questions that you have to answer to finalize the configuration of this system, starting from what would be the type of your reactor. So as you remember from your reactor engineering course, there will be a couple of options for a type of reactor, starting from probably a batch, and then you have the plug flow reactor, and you have the continuous stir tank reactor. You have to link all the information provided in the case study to make sure that you choose the correct or the appropriate reactor type. And then later on, we have also to select the correct operating pressure and temperature for this reactor. Okay, so we want to produce DME at 5 tons per hour. So that's quite a large capacity. So it's not really a good idea if we want to consider the batch reactor process. Okay, so we can cross this option, and then we have to think about Pfr versus Cstr. What's the main difference between these two types of reactor? So I'll give you the quick illustration. For the Pfr, it is called as a plug or pipe reactor. So that's your concentration in the inlet for a Pfr. And the difference is, if you have a stir tank reactor, that will also be your inlet concentration, and that's your outlet concentration. So what's the difference? For the pipe reactor, the assumption is there will not be any mixing into the axial direction. In that case, you can imagine that we have the concentration of the feed entering at a very high concentration at about 99.2% mole of methanol. If we put it into the pipe or the Pfr reactor, those concentration will decrease gradually along the way. So starting from 99.2% and then probably decrease to 95%, 90%, 85%, and so on, up until the very small concentration at the end of those reactor. Let's say it exceeds at about 10%, for example. And that's very different if we use the Cstr for the same reaction. What's going to happen is, when you put the concentration at high concentration, 99.2%, and then because of the characteristic of the Cstr, perfect mixing. That means once it enters, directly it will be mixed together into the equilibrium concentration inside of the reactor. So it's not going to be decreased gradually. And we have to imagine how would those phenomena affects the performance and the size of our reactor. And luckily, we already have the power law kinetic expression as provided at the top of your screen. You can see that it is a first order of gas reaction. And our objective is to make the reactor as small as possible, so that it's going to be as cheap as possible. How can we do that? Okay, to make the volume to be as small as possible, we have to make the residence time inside of the reactor as fast as possible. To do that, we have to make sure that our kinetic rates to be as high as possible. And you can imagine we have a first order of reaction as a function of the partial pressure of the methanol. Partial pressure is directly related with the concentration. Okay, so if you maintain the concentration to be as high as possible, as in the PFR case, that will also help our partial pressure to be as high as possible. And as this is a first order, if we keep this partial pressure as high as possible, that will help the kinetic rate to be as high as possible. So, in short, in this kind of process, because it's a gas phase reactor and a positive order of reaction, first order, it's very easy for us to say that PFR is the correct type of the reactor. Okay, and CSTR, it's not a correct reactor. Probably it's gonna be more suitable for a liquid phase or even a negative order gas reaction. So I hope that explains very clearly the reason why we choose PFR. So I'm going to directly update the PFR to represent our selection. So that will be a packed bed, adiabatic filled with catalyst. Okay, so let me erase those additional explanation. Okay, so we finished the explanation for the type of the reactor. Now we go into the operating conditions of the reactor. What will be the pressure and the temperature for this system? Again, check the stoichiometry provided in the case study. How the pressure will affect the performance of the reactor. Remember your basic chemistry. How the pressure will affect your equilibrium. For a gas phase, it will depends on the mole in the feed parts and the reactant parts. Okay, in this case, we have 2 moles of gas in the feed side, and we also have 1 + 1 mole, which is 2, in the product side of the reactor. That means we have isomolar in this case, 2 mole and 2 mole. In that case, the pressure is actually will not affect the equilibrium of your reaction. So let's say that for now the pressure can be flexible because the equilibrium will not be affected much by the pressure. Okay, maybe it will follows the pressure of the subsequent unit of operation, such as distillation. And then the last question, the temperature. Again, use all the basic fundamental information. This is an exothermic reaction. What does it mean? It will generate heats. And if it's an adiabatic reactor, as will be modeled in this case, adiabatic means we don't exchange the heat from the system to the environment. That means if it's an exothermic reaction, the heat generated will be used to increase the temperature along the way of the reactor. And actually, if you look very closely at the previous video about the case definition, we already give you a hint that the temperature has to be limited at certain point to limit or to prevent any catalyst deactivation. But before we go to that number, it's important for us to remember exothermic reaction, how the equilibrium will shift if the temperature change. Okay, so for every reaction, we have to consider the equilibrium and the kinetic. How will it change specifically for our case study? For the equilibrium, exothermic. That means if the temperature increase, what will be the consequence? The equilibrium will shift to feed part. And that's not really a helpful thing for us. Temperature increase for exothermic, equilibrium will shift to feed part, to methanol part. So the conversion may not be 100%. But the cons at high temperature would be for the kinetic. If the temperature increase, the kinetic rate will increase. Okay, why? Again, I think for most of the reaction, every time you increase the temperature, the constant of your kinetics will increase, and that will help your reaction to happen very fast, small residence time, and small volume. So we have pros and cons over here. Do we want to prioritize the equilibrium, or do we want to prioritize our kinetics? And you can also imagine the opposite options, when we want to keep the temperature as low as possible. In that case, if we keep the temperature as low as possible, the equilibrium will shift to the product side. That helps you to gain a high conversion. But the problem is, at a low temperature, the kinetic rate will decrease, and it will require a very big reactor and very costly. And that's not really our preference. So we have some probably experience from a lot of chemical reactor design in the plant that we want to prioritize the kinetics so that the size could be small. If we have some drawbacks in terms of the equilibrium at the high temperature, we can compensate those in the other unit of equipment. For example, let us focus on the option of this one. We want to keep the temperature as high as possible. The kinetic rate is fast. The equilibrium cannot achieve those maximum numbers, so the conversion cannot be 100%, but we can compensate it by the addition of the separator, and the unreacted feed can be sent it back to the reactor. As explained in the previous video, that's the generic structure of chemical plant. So in this case, we will prioritize to increase the temperature as high as possible. But again, the question is, what will be the limit? The answer already provided in the previous video about the case definition. It will be limited by the temperature of the catalyst deactivation, which will happen at about 400 degrees C. So in that case, we will limit the temperature condition. It will be designed such a way that the temperature will exit at about 365 degrees C, and it will enter at about 250 degrees C. Those increase will be happening because of the heat generated by the exothermic reaction. Okay, so all the main question in the reactor has been answered. So let me erase this to make it more focused for you. So the temperature will be between 250 to 365 degrees C. Okay, let's move on into the next layer in the onion chart, which is the separation process. Okay, you have to imagine that we're working with three components over here. We have the methanol at the feed parts, we have the DME, and the water. Okay, so we have three compounds. If we want to perform a basic simple distillation, that means we need at least 2 distillation units to get 3 pure products. And you have to remember what will be the order of the compounds in terms of the boiling point. We know for sure that water will be heavier than methanol, because at ambient pressure, the boiling point of water is about 100 degrees C, while the boiling point of methanol probably around 60 degrees something of Celsius. How about DME? Again, you can check HYSYS, you can check any thermodynamic books, but the easy way to imagine it is DME is a substitute blending for LPG. LPG, you can find it at ambient pressure, ambient temperature, that's going to be in vapor phase. That tells you that the boiling point will be below those ambient temperature. Okay, so it's actually close to -20, -30, or even -40 degrees C, and that tells you that the ME will be the lightest component out of all these components involved in this case study. So we can use those information to design the distillation column. Okay, so let's say I have my first distillation column. I will have a top product. Your top product of your first distillation will be the lightest compound. Again, that would be your DME. So let me add the condenser. And that's the reflux. Okay, what will be the bottom products? So the bottom products after the reboiler, that will be the mix of methanol and water, and that will be sent to the second distillation column. Okay, now remember the order. Methanol is lighter than water. In that case, we will have the unreacted recycled methanol at the top of second column, while we have the water as a side product from the bottom of the second column. Okay, so that's the sequence or the configuration for the distillation. Again, you have to ask this main question: what will be the type distillation, what will be the pressure, what will be the temperature, using all the information provided all in this case study. Okay, so this is the hierarchy or the procedure to design a distillation column. First, we have to set the operating pressure at the top. Okay, so the order will be, first we have to set the P at the top. Using those information, we will set the correct bottom pressure, and then later on we will define the feed pressure. That's the third step. Pressure of your feed. Okay, but again, it always starts from the top. Why? Because it's actually very depends on the utility available in your plant. That's why we provide you the informations about the cooling water availability, which enters your system at 30 degrees C and exits at 40 degrees C. Why? Because you can imagine from this condenser and reboiler, which one requires cooling water and which one requires steam. The objective of condenser is very obvious. It's to change the phase, the top product from the first stage, so that you can get a liquid product, because that's stated in the case that you want to get a liquid DME as your product. How to do that is you put a cooling water. So I'll put the number directly, 30 degrees C, and then it will leave at 40 degrees C. Remember the principle of heat transfer. The heat will always happen from hot temperature to low temperature. There is no other way around. Okay? Do you want to absorb heat or do you want to release heat? That's the important question. In order to condense the vapor, that means you have to release the heat. If you want to release the heat, that means the direction of the heat transfer will be from the main process to the utilities. That means your top temperature has to be hotter than the cooling water. Okay? Your temperature at the top has to be hotter than your cooling water. So that's the temperature of your cooling water plus extra tolerance for the heat exchanger, the log mean temperature difference, for example. In this case, we already provide you the information that the cooling water will enter at 30 degrees C. So let's say we want to give 15 degrees C for the delta T at the heat exchanger, so that we know the top temperature for our first distillation column will be around 45 degrees C. Okay? Using this information, then we fill out the rest of the information. We want to get DME as a liquid. That means the vapor fraction will be 0, a saturated liquid. And if you remember from your thermodynamic course, if we know the compositions at 99.5, we know the vapor fraction, it's a saturated liquid. We know the temperature is 45 degrees C. We can calculate the bubble pressure. Okay, and that can be done very easily using HYSYS. So I'll switch the window now so I can help you to make the dummy stream for this product to help you getting the correct top pressure.
So this is the demonstration to select the distillation pressure. So I will use the starter from the previous video where the components already added into the simulation, methanol, water, and DME. And the fluid package, we already selected non-random 2 liquids for the liquid parts and the Peng-Robinson for the vapor parts. So I can go to the simulation. Now I'll go to the view and then palette. Again, this is only to help you with the dummy stream, so I will not install any equipment. I'm going to add a stream and then double click. Let's say I set it as DME, dummy, and I will add the compositions required by the project. In that case, the DME has to be 0.995, and the impurities will be methanol, because that's the next heavier component, not water. After that, I check the component already 1. You can double check by click the normalize. Okay, and then after that you can see that the status already changed to unknown temperature. So now I'll go to the condition. Again, this is to illustrate the top product of the distillation column. We already selected that it's gonna be a total condenser. In that case, it will be produced as a liquid, so the vapor fraction will be 0. Saturated liquid. Okay, temperature and the pressure. Again, the objective is to get the pressure. So what we need to do is to select the temperature. In that case, we already decided that it will be the temperature of the cooling medium plus some delta T. In that case, the cooling water temperature is 30 degrees C, and we add another 15 degrees C for the delta T in the heat exchanger, so I will put 45 degrees C. And then we can know that the bubble pressure at this condition will be 994.5 bar. So I will use this number back into our board to use as the top pressure of the distillation column.
Okay, so from those demonstrations, we get the value now for the top pressure. Okay, the number will be around 9.95 bar. This is the bubble pressure at the required purity, 99.5%, at liquid condition at 45 degrees C. Using those information, now we get everything we need at the top. So we move into the next part, which is the bottom. The pressure at the bottom will be calculated as the top pressure plus the pressure drop. Okay, so we have around 9.95 bar provided in previous calculation plus the typical pressure drop in a distillation column. So let me help you with the quick value that is typically happening in the distillation column. Probably it's going to be around 0.2, 0.3, or at most 0.4 bar. I'm going to give you the explanation for those, so let me use one number just as a starting point. Okay, let's say I'm going to give extra 0.2 bar as delta P, so that I will get the bottom pressure as 10.15 bar. Now the question is, where is this number coming from? And you can answer those questions by imagining what will be the pressure drop for the vapor when it enters the bottom of the column. Okay, so you can imagine once you reboil the bottom stage, now you get a vapor, it will go to the top, and what will be the restriction for those streams to go to the top? In order to make it easier for you to understand, I will make another diagram of a distillation column. So let's say that's my main distillation column, that's my reboiler, that's my condenser, and we know that the distillation column is mostly a tray column, okay, or even some pack column for some special application. So let's say I'm going to use the illustration for the default tray column. Okay, how the column will be filled inside of this column? Okay, we have a tray, but you will also have a lot of fluids going on. Okay, vapor goes to the top, liquid goes to the bottom, but it will be filled by a liquid. This is what we know as a liquid holdup. At each of the stage, there will be a certain thickness of liquid holdup. And if we have the accumulation of those liquid holdup, we will have a hydrodynamic pressure inside of the column. Okay, so actually the pressure drop, the easiest way to calculate it is by calculating the hydrodynamic pressure. It's the density times the gravity constant times the accumulation of the liquid holdup. Okay, so just for a quick calculation, let's say it's close to water, so 1000 kilogram per cubic meter times close to 10 meter per square second. And what will be the head? Let's say we want to have a simple distillation with 20 stages. Each stage is probably around 0.6 meter or 60 centimeter, but the liquid hold up, the red line, let's say it's about 10 centimeter or 0.1 meter. Using those numbers, we can combine it, 20 stages times 0.1. So now I have around 20,000 Pascal, which is around 0.2 bar. So that's the simple explanation why we will get a typical pressure drop in the distillation column for about 0.2 or 0.3 bar. Okay, let's go back to our main flow sheet. Okay, bottom pressure done. How about the bottom temperature? Again, this is very simple. This is your product will be produced at a saturated liquid condition after the reboiler. So that will be the bubble temperature at this pressure at the required composition. Last, feed pressure. Again, the order, the top pressure will be the smallest, and then the bottom has to be higher to accommodate the hydrodynamic pressure. The feed pressure has to be the highest among those three pressure conditions. Why? A simple explanation. Remember the fluid mechanics course. In order the fluid can be fed into and can be flow into the downstream process, the pressure at the upstream has to be higher than the pressure at the downstream. So if you have a bigger pressure in the feed, the stream will go as you're expected. But once you have pressure less than your bottom pressure, it will happen a reverse flow. That's not our purpose. So let's say our feed pressure now has to be above 10.15 bar. You can round the number. Let's say I'm going to use 10.5 bar. Okay, how about the temperature? How about the temperature? What will be the temperature for your distillation column? You can imagine from the previous unit of operation, we have the exit gas of the reactor at about 365 degrees C. And this must be a superheated vapor. Why? Because even it already enters at 250 at the gas phase, temperature increase for another 115 degrees C, so it must be a superheated vapor. What will happen if you force this stream goes directly into your distillation column? Superheated vapor, that means all the feed will goes to the top. And that's not very helpful for our distillation column, because the essence of the distillation column is to contact the vapor and the liquid. Okay, if you have this superheated vapor coming into your distillation column, it will result in a very big condenser duty, because every feed has to be condensed. It will result in a very big diameter at the top of the column, or even worse, it cannot be converged. Okay, so you have to decrease the temperature. You have to change the phase. Okay, that's why between the reactor and the distillation column, now I will add another equipment, which is a cooler. And the purpose is to decrease the temperature to make it easy for our distillation column. So again, the question is what will be the temperature? But we actually have another option. If we don't know the correct number for the temperature, we have another option to define our vapor fraction. By defining the vapor fraction, if we set it as 0, that means it will enter the distillation as a saturated liquid, because the vapor is 0. If we set the vapor fraction as 1, that means we put the feed into the distillation column at saturated vapor. But the rule of thumb, or maybe the quick way to help your distillation column, we're going to give the vapor fraction around 0.02 to 0.05. Okay, so that some of the vapor will directly goes to the top, and most of the feed will goes to the bottom. and that helps your equilibrium inside in the distillation column. Okay, the top conditions already finished, the bottom conditions it's finished, the feed condition, pressure, and vapor fraction, that completes the material balance. So we can move on into the next layer in the design and in the onion chart. The third layer would be heat integration, but we can see from the flow sheet that it's not starting from our feed. So we already prepared the reactor, we already prepared the separation, we already prepared the separation preparation, but we actually haven't defined the feed preparation. What we know is the feed will be provided at 99.2% mole at ambient pressure and temperature. Okay, I have my feed over here. It is still at ambient temperature and pressure. It has to enter the reactor at 250 degrees C. Okay, so it must involve some heating process from 30 degrees C to 250 degrees C. Okay, so let's say it's 30 degrees C, 1 bar. What would be the feed preparation to prepare before the reactor? So it involves some heating and it will involve some compression. Why? Because it is stored at 1 bar. We haven't decided the pressure of the reactor, but now actually we already know the pressure of our distillation column. It's around 10 bar, it's around 10.5 at the entrance of the distillation column, and we can calculate backwards from those information. For example, now this is your shell and tube heat exchanger. Let's say I'm going to use a typical pressure drop. You can again refresh your heat transfer course, but I'm going to bet that the pressure drop will not be higher than 0.25 bar. Okay, so let's say I'm going to use 0.2 bar. This is a reactor. Then the delta P should be higher than the heat exchanger. Why? Because it's filled with catalyst. So it's a solid gas interaction. So maybe we don't know the correct number for now. I'm going to give some big number to make it safe. Let's say 0.5 to 1 bar. Okay, what else have to be considered? So what I know for now is I have option to pressurize the liquid feed and then vaporize it before it enters the reactor. Or I have my second option. My second option is I will vaporize it first to prepare it into the gas phase, and then I will compress it using a compressor. Which one is the optimized one? For this one, you have to remember again the thermodynamic and the fluid mechanic course. Okay, what's the main difference between a pump and a compressor? One is dealing with a liquid, which is an incompressible fluid. One is dealing with a vapor, which is a compressible fluid. Which one would be more energy efficient, which would be cheaper to be performed? And actually, the answer is this option will always be cheaper at the same capacity, at the same pressure ratio. Why? Because if we're compressing a liquid, it is an incompressible fluid. That means almost all of our work provided into the system will be used to increase the pressure. Without increasing the temperature, without decreasing the volume, almost most of them will be used to increase the pressure. That will not happen in the compressor. It's a compressible fluid. That means the temperature will increase. That means the volume will decrease, and that requires work. So only some of your work will be used to increase the pressure, which is your main objective. Okay, in that case, pump will always be energy efficient, will always going to be cheaper, will always be easier to be operated. So now I can delete my second options, and I put those selected configuration to my main flow sheet. So I will have a pump, and then remember you have a recycled stream. So now I'm going to add a mixer. and then after that I add the heater. Okay, in that case I can link my recycle stream back into my mixer. Okay, so the flow sheet almost done. Now we just have to focus on the operating conditions. We have to set what will be the pressure of the pump. Okay, to make it consistent, what will be the pressure of the pump? What will be the pressure of the reactor? What will be the delta P in the heater? Okay, the delta P, again, this is another heat exchanger. I can use the same number of the default delta P. Okay, what about the temperature? We know that the temperature of the reactor has to be 250 degrees C. So we know the temperature of those outlet heat exchanger. It enters at 30 degrees C, it exits at 250 degrees C. Okay, so now we just have to accumulate all those pressure number into the pressure of those pump. So quick calculation, 10.5 times 0.2, 10.7, plus 1, 11.7, plus 0.2, 11.9. So it's close to 12 bar. Let's say we want to round that number to provide additional pressure drop for all the pipeline, for all the fittings, even for the elevation. Remember, this is all will be in the ground level. Once you send it to the distillation, it could be sent, let's say, to the top. Let's say it's 20 stages, that's 12 meter. That means we have to provide another 1.2 bar, roughly. So from those 12 bar, maybe I'm just going to round the number to 15 bar, just for starting point. Okay, so it's done. Delta P is provided, temperature is provided. Delta P is provided, temperature is provided, pressure is provided, vapor fraction is provided. So we finish almost most of our main equipment. We haven't discussed about the second distillation column, but I hope you can perform the same exercise with the first distillation column to set what would be the top pressure, what would be the bottom pressure, and what would be the feed pressure. Okay, replay this video and then perform the same exercise. Hopefully now you know the temperature of your second column, and if it's lower than your first distillation column, that means it's likely for you to have some valve to reduce the pressure. Okay, check again, top, bottom feed. What will be the purity? It has to be 99% of methanol. Okay, 99% of methanol at required utility availability. So if it's a low pressure, it will be sent back to the initial part of the process. Remember, this is 15 bar. And if it's a low pressure, it must be lower than 10 bar. Then you have to add another equipment, which is a pump. So that's our recycle pump. Let's say now the pressure has to be 15 bar as well. Okay, so I guess we have everything done for the purpose of this video. We finished the flow sheet, we finished all the main operating conditions. So now we're ready to start to build the simulation in HYSYS in the next video.